All right, today we want to talk about a little bit how to solve system of differential equations in general with additional analytical method, but this only works for specialized systems. So basically, for a general system of differential equation, it's going to be challenging to solve it, especially when it's not linear. Okay? But then, today, we want to solve two special systems which are slightly simpler than the fully capable system of differential equations. The first one is called completely decoupled system. The idea is quite easy. That is, you have a system which looks like this. Yes, you do have a system. You have two species together, but what you need to notice is x, the first one only involves x, and the second one only involves y. Therefore, there is no interactions. Between x and y. Solving them together is the same as solving each one separately. So x changes according to its value, not with y. Y changes according to itself without x. So putting them together or not putting them together really doesn't change the way you solve it or ever change their value. Therefore, you can solve them separately. A typical example is x prime equals y. X, 1 minus x. So you have a logistic. Y prime, you will have something called 0.1y. From here, you can see putting them together really is the same as just solve 1 and 2 separately. Okay, you solve it by logistic. Solve by exponential. Okay, so this is completely decoupled system. You put them together, you put them separately, really doesn't change the way you solve it. You can find the separated solutions of each one, and then when you finish, you basically just write the solutions together. Or you don't write the solutions together, just treat them as two separate systems. There's no difference. Okay, the second one will be slightly harder than this, but also not as hard as the full system there, which is called partially decoupled system. So they're not completely decoupled. That means x, y, they're not completely unrelated, but you only have one direction relationship. For example, x depends on x and y, but y only depends on itself. Or it's the other way around. So usually, you should have x, y depends on each other, but if it's only one direction, it's either x depends on y or y depends on x. Okay. Then what you can do is you can solve one of them, because this one does not contain x. You can solve it first for y, and when you finish, you plug y back into the first one. Since you already know the solution of y, you can actually solve the whole thing as a function of x, as an ODE of x. So let's see a quick example. From here, you can see, well, if x depends on y and 1 depends on x, we have to solve them together. But for this case, you can clearly see 1 depends on 2, but the 2 is self-contained. Then what we can do is we can solve for 2 first. There's no x, only y. Therefore, y equals a constant times e to the negative 4t. And once you finish, what you can do is you can plug it back in 1. You have x prime plus 2x equals 2x. Okay. Before, you have a y, but now you know what y is. That's going to be e negative 4t. After that, you solve this one, and there's no more y anymore because you already know what y is with a constant c. You can solve it as a differential equation of x. Okay. From what we see here, it's pretty easy. It's a linear system. Therefore, we have a integrating factor mu t equals e integration -2 dt, which is e to the -2t. Therefore, e to the -2t x prime minus 2 e to the -2t x equals 3c e to the -60. Okay, you combine -4 and the -2t together. This clearly gives you, okay, check your work. The first one gives you x prime, the second one gives you the prime of this, which is -2 times itself. Equals 3c e -60. Now if you take the integration, okay, -1/6. You have a plus a constant. This time you probably want to do d instead. And then your x is nothing but 3c, so -1/2 c, which you can just replace by c. This we can just call it c. Okay, plus d divided by that, so it's gonna be d e positive 2t. Or you can simply write them to be constant 1 and constant 2 if you want to see it more clearly. Okay, so that would be the solution we get from the partially decoupled system. Because it's partially decoupled, that means you have two equations, but the first equation is self-contained, or the second equation is self-contained. Okay, whichever one, you just solve the one which is self-contained for one variable and plug it back into the other one, so you are going to solve it again as a ODE with only one variable, one after another. And if you have one constant, just keep it, okay, and give the new constant another name. So that's it. That's how we do a linear partially decoupled system. Okay. Of course, the ultimate challenge is going to be when x depends on y and y depends on x. Okay. The third thing we want to quickly do is we want to introduce you, like, if we're solving a linear system, which means a system of ODE with only linear constant coefficients. -2y. We can easily see that this one actually corresponds to okay, which is completely decoupled. And this one, when we have 2x plus 3y, -4y, okay, this one clearly can be rewritten as this. From here you can see, okay, completely decoupled system basically corresponds to a diagonal matrix. Completely decoupled. Of course, I'm only talking about linear systems. Okay, for other systems, there's no way you can write them into a nice matrix format. Okay, and partially decoupled system corresponds to triangular matrix. It may be lower triangular, maybe upper triangular. Correspond to partially decoupled. Of course, a general system should be a general matrix where the four entries are all non-zero. So from here you can see the coupled and the completely decoupled and partially decoupled are the easier cases for when you handle matrices. So of course they're easier to handle. Okay. All right, that will be all we have for the special systems. Completely decoupled, which is the easiest. Partially decoupled, which you can do them by steps, which is still relatively easy compared to the full system. All right.